let's see how we can tweak our random walk model in one dimension to describe motion in two dimensions. Well, if you recall, we described the x-coordinates along a number line with a simple difference equation, the old position plus some random change, which came from a normal distribution, equals the new position. Well, if we want to describe motion in two dimensions, then we need the state of the location needs two components. We'll need x and y components. And we can actually just adapt this very easily. We'll just say the new y coordinate is equal to the old y coordinate plus some change in y. And we can add, again, random changes according to some distribution. Okay, so that is going to give us a two-dimensional random walk. And since you already saw me code that out, let me just skip ahead to the code. All right, so here's how we could implement this. We could, first of all, I'm going to actually keep track of all of the results. So I've created some empty matrices to store all of the different experiments I'm going to run, as well as all of the individual steps within those. I'm going to start at the origin, 0, 0. And what we'll do is we'll just generate a list of random numbers for the changes in x, random numbers for the changes in y. One by one, we will add those changes in x and changes in y to the previous position, and then we will store those in our matrices. All right, and if we do that, I'm going to insert an error really quickly because I don't want to do the last part of the code. I'll just do the first part. All right, you see here's a bunch of trajectories in two dimensions. Again, this is just our little person is wandering around aimlessly in the xy plane. And the axes here are not time and position, but rather x position and y position. So if you want to actually see how they evolve over time, you need a third axis here, but I decided not to show that. All right, so we've got all of those displayed, and you'll notice that when you do the random walk in two dimensions, again, the trajectories seem to be a little denser in the middle, close to the origin, and then every once in a while you go far away from the origin, but most of the time you stay a relatively small distance away. And so what we could do is we could actually plot a histogram of the distance away from the origin at each given time. And so let me show you what that looks like. All right. And so initially, after one step, let's fix the labels there. So after one step, it should look like this. All right, so after one step, most of the time we're within 1 unit of the starting point. There's some probability that we're multiple units, more than 3 units away, but that's very, very rare. However, after 10 units, you'll notice that things have spread out a little more. Being more than 4 units away from the start is not at all surprising. That happens quite frequently. And then after 100 units, most of the time you're more than 4 units away. And so what this simulation of a random walk allows us to do is it allows us to ask questions about location. It allows us to say, what's the probability that you end up a given distance away? What's the probability that you reach a particular point or cross a particular line? If you have multiple agents, you can talk about what's the probability that two different agents are going to collide with each other or cross paths. And so we can take this idea of a random walk and add all kinds of wrinkles in it. You can introduce barriers so that maybe instead of just wandering around randomly in an open space, the agents are wandering around within some enclosed space. So if you're simulating people exiting from a building, you could have walls that limit where they're able to go, and that would just amount to restricting the motion so that when you add those changes, you don't cross a wall. You can add people interacting with each other, and maybe that means that people are either gravitated towards one another or they are repelling to each other. So you could adjust the random changes that you incorporate so that they are biased in some way toward or away from each other. And in this case, we used a symmetric distribution. We used a bell curve, which was even on both sides. But maybe you could be more interested in a biased random walk. So for example, suppose that our walker actually prefers to go north, meaning the y-coordinate should increase, but there's some probability that they'll go back as well. Well, we could do that by taking the noise and shifting the mean so that on average, our change in y is positive. And similarly, we could also adjust the standard deviation. So let's do that really quickly here. First off, let me change the labels. So they're actually correct. All right, when we added our change in position, right now we're using a random normal variable, which means the average is 0. But let's suppose that we would like the person to be biased towards moving north. Well, in this case, if I add a constant, like 0.5, then on average, we're going to move 0.5 units north, and but we'll still have some random possibility of going south. Okay, we could also adjust the standard deviations. So the standard deviation of a normal distribution is set to be 1, but if we multiply by, say, 2, then we've doubled the standard deviation, and if we multiply by a half, we've shrunk it. And so let's say that we want to go north, so we're not going to have much variation in x. So I'm going to make the standard deviation there 0.1, and then I'll make the standard deviation of my second, my y coordinate, make that 0.5. All right, so they're going to move north or south, but not quite as much as before, or the variation is not going to be quite as much as before. And let's see how that changes the picture. All right, and so we will run this, and I'll just comment all of this out since we don't actually care about that. And you notice now the motion is still random. However, most of the walkers are ending up far north of where they started, and that's again due to the fact that we changed our probability distribution for the change, and so they are biased towards walking north. All right? And now I show you these examples not just to say that we fully explored random walks, but just to give you a sense of some of the options that are out there. Modeling stochastic processes is an incredibly powerful tool for describing a wide variety of different phenomena, and random walks are the tool that we will primarily use when you want to incorporate spatial information. And they can also be useful for other types of scenarios as well, which we mentioned stock prices in the previous video, and that's one of many applications. All right, and so one way of taking this idea of a random walk and then combining it with some of our other models, like epidemic models, is actually discussed in a YouTube video that I posted in the playlist. So this is by a channel called 3 Blue 1 Brown, where they do a really, really nice job of explaining how you can understand epidemics and some of the strategies used to combat them using random walks combined with the SIR model, though, that we discussed previously. And so I highly encourage you to take a look at that video. It's not necessarily something that I'd expect you to reproduce. There's a whole lot going on in there, but it takes very simple ideas that we've already talked about and combines them in a really powerful way.